those are my names, but the point here is that normally I give a presentation to give the presentation is to give you an idea. Is it just the moon we see every time it shows up in the evening? In the morning it is gone. Sometimes it shows up in the morning. By lunchtime you can't find it. Even sometimes lunchtime you find it. So it's all about the sun. This is the sun. And then we have a lineup of planets. There are a bunch of other planets that we have been able to see. Previously Pluto had been removed, but then they again included it. But also there is another planet which they have seen beyond Pluto. So in their order, I have not really bothered to make an acronym like the one I told you about last time. I haven't coined out an acronym that can be used to define these planets or to make them in order. But you could try to you can figure out what you can. But there is the nearest, the sun is Mercury. You have Venus, you have the Earth, the Mars, which they call the red planet. We got Jupiter. Jupiter has just been busted, as in they have just sent their Juno. Juno is Juno, is a satellite which they have sent there. It can take photos, it can do some measurements, it can do profiling of the nature of Jupiter. Jupiter is the big boss in the universe. And then we have Saturn with Saturn rings, we have Venus and Neptune. This is an arrangement of how these planets, spin and at what angle they spin. So we have Mercury spinning at 0.1. It tilts only for about 0.1 of a degree. Venus 177 degrees. Earth tilts about 23.4 degrees. And then you got the Mars 25, Jupiter 3 degrees. That's Jupiter only can tilt a bit. In night we will be able to see Jupiter. So you'll be able to sit and say, I got it, I saw it, so that you see these lines there. And then Saturn spins up 27, Venus spins up to 98, Neptune 30, and Pluto 120 degrees. So this other thing here you are seeing is the same as that receiver there, that pod you see with something on top. That something on top is this one here. And then early morning I made sure that I look for the moon and arranged the camera in such a way that the moon sits on the top of the receiver. This is photography. So it doesn't mean that when people say I am jobless, I don't have a job, you can just have the camera. The moon is there, and a house, a building, or a plant will be there, or a flower. You make the moon sit on the flower, and here you got the stuff which looks nice. You get the point? So it's all about how someone can be creative and take photos, so you can create an employment or a job from using the normal objects. So I don't believe in people saying that there are no jobs or whatever. So next would be just to show you the arrangement of how these planets are arranged around the sun. So they move around the sun, describing the path which we call an orbit. So the path described by a planet around the Earth is a sun is what we call an orbit. So this is the orbit for Mercury, orbit for Venus, orbit for Earth. I hope I have not confused the orders. An orbit for Mars, orbit for Jupiter, Saturn. This should be Neptune, and then Uranus, and then Pluto should be around there. But the universe is a bunch of stuff up there. So we are in our solar system. What we call a solar system is like if you have families. So you start with a family where there is a father, mother, children, and then you get another family, other families, then you get a village, then the villages, you get a district, districts, you get a country, countries, you get a continent, continents, you get the world. That's the same kind of perspective compared to when we talk about the universe. So I can just give a shot on that. So as you can see, the graphic is not so quick, but as you can see, this is how they should have completed this circle here. But this is how the planets should be moving. You got the Jupiter also describing, but we are mostly interested in this place here, which is our, this is us here, us, we, Earth. We, us, we stay on Earth. Okay? So this graphic just shows you how the planets spin around the sun. Okay? And then the data, some information about the different planets. In the order from the smallest to the biggest, then you start with Pluto. Which Pluto is being, there is a lot of debate whether it should be really there or it shouldn't be there. So you got Pluto, you got Mercury, you got Mars, you got Venus, you got Earth, then Neptune, Uranus, then Saturn, and hugest, or biggest, you get Jupiter as the huge man. But we are on Earth, so we are mostly interested in our little information. So we are about 149,600,000 kilometers from the Sun, or about 1.00 astronomical units. We are about 12.75 in diameter, 12,756 kilometers. If you change in meters, then you multiply by the, and mass, we are heavy as much as 5.972 exponential 24 kilograms. Now, somebody will say, but we are growing fatter every day. We have a bunch of people who grow fat, who grow tall, who are born. There's nothing we get from out there. We eat the plants, we shit them, we shit the food we eat, so it remains here. So this is the mass we are. We have never gotten any other intrusion. So somebody may reason out and say, but don't we get heavier at one point? We see the buildings coming up, we see construction of houses, construction of the roads. Can't we get a bit heavier? You are still getting it from Earth and it is still staying where? Earth. So that's why this mass is a constant. That is the mass. You won't find it different tomorrow, or you wouldn't find it different after a decade. Then we got the next slide is about the computer is a bit slow, so I hope I will not jump like two of them. Maybe I should get over top so that that's why I was skeptical. The PC is a bit slow. Okay. So this is our Earth, and of recent they have discovered another planet which mimics, or which looks like Earth, which is called Planet X, or Earth 2.0. It more or less looks like the Earth, probably, but it is far away. It is a couple of light years away from us. So this is just to show you how I came up with the other first photo I showed you, with the moon in the sky and our GPS, and adjust the camera so that they look as if they are. If you look at me now, if you look at me, I am here, yes. But if this box is here, you will be still seeing me, but with this one. If you move this side, then my box will cover you, the box will cover me. If you moved upwards, you will see me almost. That's the kind of dynamics of the camera, and then eventually you get something of the sort. In this presentation, I started presenting this kind of moon viewing presentations around 2014, after I had been in Pakwach in 2013. That's when I started getting interest in understanding what are the events available. So I found out events of when the moon will be very small, when it will be very big, super full moon, how will the International Space Station be behaving, where you will see it, and what were the eclipses in 2014, and then what other astronomical events that are available. The stationary showers are the spacewalks which happen to be in the skies. And then there was an eclipse in 2015 in April. I think so. It was in Australia, okay, in Antarctica, and these are the guys who were able to watch it. And one would wonder how was the photograph taken. The photograph was taken by a rising satellite. So as the satellite is coming on the horizon of the Earth, it takes a shot. And he was able to take a shot of the annular. This is, had it delayed a bit or had it been fast enough, this side will be equal to this side. And the eclipse, which shows a ring of fire around the moon, we call it annular eclipse. Annular meaning A-N-N-U-L-A-R. But this other photograph is a photograph of another partial eclipse which was viewed in the United States. And these were phases of that partial eclipse. And currently NASA, or the National Aeronautics Space Administration, NASA, is working so hard to make sure that they can do science exploration and some technologies to make sure they can go to Mars and colonize it. So this is the International Space Station, which is helping in doing experiments on how space affects human beings. And then we got these old rockets going to space. We have these robots. This is Curiosity. This should be Opportunity, something like that. I don't know, I'm not sure. But these are a bunch of rockets, robots which are there. These are satellites which are going on. This will be Orion spacecraft going there. And then this is a solar-electric propulsion satellite. And then other technologies. And Orion, which is a spacecraft, probably we shall be able to see the video for Orion. This is a spacecraft which was tested on the 5th. It was supposed to be 4th, but they couldn't because of the weather forecast. And this is how it looked like. You have 2 rockets among it, and then actually 3 rockets, 1, 2, 3, and then the Orion is just there at the tip. These ones will be separated later and go off. So this is eventually what will return to the Earth. So it didn't have astronauts in there. They had put in the computers to make sure that they can be the ones to help in taking measurements and taking a couple of measurements to show what could be the conditions, what happens, the pressure, the radiation, etc. Then they would, after coming back, they would be able to. So this is just a module of the Orion. This part here is covered with tiles for insulation. This is these are photographs about the Inspire Discover. This is the suit that will be used by the astronauts. This is the Orion itself. And this is just a graphic to show you this is an astronaut. This is a footstep of an astronaut. These are the tire marks or the tracks of the Curiosity. And this is an astronaut's helmet, and this is the suit. So NASA's journey to Mars. The journey for Orion will be, this is where Orion will be launched off. This is a launch system. This is Orion coming back in H1 Yeah, so H1 is because when an object is going through a space of ions, positive and negative charges, the speed, its speed makes them so hot that it becomes plasma. And then you see something like fire. So normally what we see is that as the space rock is coming from space and goes through our atmosphere, reaching the ionosphere, which is a space of charges, that part of those charges then gives us, I think it should be the mesosphere, then you see burning stuff. Then all of a sudden, disappear. You can't even hear whether it fell anywhere or whatever, because at that point it will have passed through its region. And it wouldn't land far, it would you have to land somewhere where it's got these parachutes, and even when it has landed, they have some buoyant like balloons around it, so it does not sink into the water. This is the surface of Mars. This is a guy doing the welding, doing the hard work, and this is the United launch system. I think launch something ULA, which is so this is a close-up of how a launch system is. ULA is United Launching Alliance, something like that. And then you have Orion here seated, and this is a close-up of Orion, how it looks like where it's seated. Another close-up, and towards the launching time. Then when they launch, when they spark it, they fire it up and it goes into space. You've got to do this around the equator so that you have the shortest distance to space. And this is how Orion goes into space. As you can see, it is already high in these clouds. And American children, kids of Americans, or let's say kids of the West, they buy them things that matter. Things that will add value. Not buying you a toy that you use to spray water on each other. It should be something that inspires you. In the morning today I was listening to one of the astronauts on BBC, and she was saying she preferred to be an astronaut when she was 4 years old. When the teacher said, draw what you want to be, she drew an astronaut. So, yes, we would always be able to draw what we have ever seen. You cannot draw something you have never seen. So the hard time when we try now to make sure that kids can be exposed to things that inspire them. Otherwise, I became a teacher because teachers were well off in my village. They had nice bicycles, they had a double start, they put on nicely. If they are in the quarters, they had a big chunk of land for tilling or for digging. So maybe that's what made me stick to being a teacher. But this is a toy for American children to inspire them into space. This is an actual photograph of Orion in space being tested. This is rocket propulsion here. It's still got fuel around here to propel it to float, or you can use only this part with the solar panels to generate electricity to move it. But the actual Orion is here. This is the part that goes off. So this is when it has detached already. We go with the part which is using these solar panels. Once you are above these clouds, you no longer have any shadow. There are no trees there to cover you up. So you are comfortable. You are sure that you will be able to move at will using the electricity. So all the sunlight will be able to be with you. And then you can use that word that you saw my photos near a Kayola bus, which uses solar energy. So once you have all that power, you store it in the power bank, and you can still fly anywhere you want. So eventually, this would detach itself off on the point at the point of return, when it is going to come back for landing. And it will be okay. This is its nature. We call it a capsule, and then these are tiles for heat resistance. Because if you were to be in a car and you put your hand outside and you leave it there, you would feel your hand is even going behind. And these are just air particles, air molecules, which are just here. Assume now this hand which is there is in a bunch of electrons and positive ions, and it is going through them. That means those ions will eventually make it heated up. If you chopped your hands like that, you feel the warmth on the hands. Meaning that anything, when you have kinetic energy lost into something, that energy has to be changed to something. Because we know that energy is never lost. It can only be changed from one state to the other. And then this is how this Orion looks like when it is moving through those ions. Then it causes this kind of plasma around it. And how they launched it from the United States here. You see it is almost near the equator, when I say around the equator. So it's hard to make a journey around the Earth and then try to go deep into space to make sure that now they can get an experience of where it's going. And if you drew a graph, this is how it would go like. And it was more or less like a textbook, whatever, because Orion first test in December, it was a critical, significant step towards sending humans further into space than ever before. This test will evaluate launch and high-speed re-entry systems such as avionics, attitude. Attitude control is when you tilt your phone and then the screen goes the other side. And then parachutes for landing and the heat shield. So this flight test was to test a lot of stuff. What material can give good heat shield or heat resistance. So this is how it looked like when it has just come back compared to before launching. So it heats up. These are the same photos almost. They don't look the same. If you look closely, this is not the same as this, but the most important thing is about the heated up thing. The banter, they say the banner. This is how Orion comes and can put off the panels and comes and docks on the International Space Station. This is the International Space Station. We shall see a video. This is how it looks like. And so this is Launch America Commercial Crew Transportation. The mission is in sight. Soon, people who have a lot of money will be able to pay. He goes in the space shuttle, goes to space like for a week. Also enjoys, runs around, takes selfies when he's hanging in space, and comes back if they get the money. So that's what you hear the word of commercial crew. So far, NASA does it for research. NASA has been doing all this, sending astronauts into space. It has been for research, not for purposes of. So this is the artistic impression of how Mars exploration will take place, or colonization. Astronauts moving around with robots, trying to do experiments, having a station where they are staying with communication gadgets for sending back the information, and other robots to get them along the way. These are some ladies who are astronauts for purposes of ladies being able to be attracted in space. This is Mars rover, the about 1 ton rover or robot which was launched to Mars. It has a laboratory, it has these tires here, it has this robotic arm here which took the photo. It has the eyes here, it can send a laser and try to figure out. It can use its system here to pick some soil sample, drill it and take it in there, run some. But it doesn't do it itself. Somebody on Earth, on the control in the United States, is able to send some information, some commands. So commands it just like when you're on WhatsApp, you can say hi. You've typed hi on your phone. My phone vibrates, and then I get to know that you are saying. If you send a joke, they will see me smiling. The same thing. So you send a command when you are in the United States, it goes to the satellite which is orbiting the Mars, and then that satellite sends it to Curiosity. Curiosity does what you told it to do. It drills the soil, it puts it in the lab, processes runs a test, then produces results and sends the results. Or you tell it to take a photo and you make sure it covers this much, it takes the photo, sends it through a satellite, from the satellite to the Earth. Okay? So there is another shot, now Curiosity facing us and the clarity of the equipment all around here. And this was Mars, this is Mars as of today, just the way we draw the Earth. And you see Africa here, the United States, Asia, Europe. This is the globe of Mars. But this is how it looked like in ancient times. So meaning that maybe we've been so careless that we have spoiled it. So so that we've lost all this water. Maybe if we continue being careless and being irresponsible, Earth may also end up being like Mars, becoming a desert. After all, in the north and the south, it has already started. These are all technologies that are on Mars, around Mars, taking different information, and if you were to be keen, you would be able to read each of these and what it does. This is marine and some marines and some marina and something. This is so each of these satellites take different information, and each of these robots here take different information on the surface of Mars. I will focus on the rocks. So these are the rocks on Mars, how they look like. On a scale of 1 centimeter, this is how you will have, this is about half a meter. So this rock is about half a meter. This is a close-up of the given rock on Mars. This is other rocks and a little bit of landscape on Mars. This would be this should be able to play, but it wouldn't play. This is a sunset on Mars, and the video can't play because I didn't put it in. I was supposed to put it on this computer to be able to play. Okay, so this is the landscape of Mars, and this is another landscape. And just like you can take a photo of the same place but looks different, okay? But these are definitely two different places if you look at them closely. Okay. Then you have another photo of the landscape of Mars, but with a close-up of a couple of rocks. And this is a selfie taken by the Mars rover, Curiosity. So it took a selfie like the craze around. The time they took this selfie is the time when selfies became selfies, when it was the talk of town. So the controller here on Earth also sent a command and said, made it to turn and take a given angle, and gave us a selfie. This is Mars surface, but with what we call aurora. Maybe I will try to explain what an aurora is. This was Messenger, and Messenger was supposed to be on, this was as of August of 2014. It crashed into, I think, Mercury, and these are statistics of what it had done, the information it had got. It had 6 flyovers on the inner planets. It had 35 million shots by the Mercury laser altimeter and EDC. So it was trying to orbit Mercury and trying to look at different things. These were astronomical events in 2015. I don't have those of 2016, but probably soon I will be able to update them. In 2015 there was an eclipse. I think you should have seen it around this one here. And this eclipse here was in parts of Sweden. Okay, even Norway they were able to see, but Svalbard islands are ones who saw the total. So where you see red, that's where the total eclipse is. Here you're seeing the total eclipse. The ones which are orange are more than 9%, yellow, dark yellow 9%, yellow 40%, the other ones not visible at all. So all these countries, including Uganda here, we didn't have to see anything. Okay, we didn't see anything at all. Okay? So the eclipse, you could have another graphic to show you where you see this black dot is where actually the total eclipse passed by. And this is the part here that was able to see a total eclipse. So anyone who could have been in a plane flying around here could see an eclipse without even fearing the clouds. You can do that above the clouds. And unlike you guys here who just hear an eclipse and don't care, in the United States, in the Europe, these are Norwegians. They were busy taking photos all through. You can see each and everyone has a camera, and they are deep into snow, and they are comfortable and willing to watch. This is how an eclipse, a total eclipse, looks like. The sun is behind there. The moon is able to cover the sun, because if you see me, now you can see part of me. Okay, now you can see me with this covering just the nose. If I was to send it there, continue sending it there, eventually it will cover the whole moon because of relative distance. So if you put your box in front of you, you wouldn't see nothing about me. If you push it away from yourself, you start seeing parts of me. If you could stretch it magically up to my nose, it may even maybe cover my mouth. So that's how the moon is able to. At this point of eclipse, normally the moon is about 400 times nearer to the Earth. And if it is about 400 miles nearer to the Earth, it means that it is able to cover the whole sun at the end of the day. But this is what we call the corona part of the Earth, of the sun, that you are able to see these lights coming out like that. And when the moon is approaching the sun, it means that if it was to be going away from the sun, you start by seeing the diamond ring, then eventually it becomes part of it. So if you are very good at taking shots, photographs, you can get a nice shot of the actual diamond ring with the shiny part on the top and the other part of the ring. Okay, this is a shot which was taken with the moon partially covering the sun on an eclipse, but the most interesting part was these other images, the time-lapse or lapse images, where you take shots after intervals. So these were intervals of the International Space Station going around. The International Space Station is just a chunk of modules, some components, some housings put together, and then they are hanging up there 220 miles in space, 220 miles above the sea level. I'll show you what it is. So this International Space, okay, before I go to the International Space Station, the issue to do with the night and the day, and issues to do with eclipse and the like, it's all depending upon the sun, its sun rays, then the earth and how it spins. So the earth spins like that, here, and this is the equator where we live. Okay? And we have seasons because of the sun, the earth's movement, and this earth movement depends basically on as it is going at a given particular time, it is at a given position, and if you add on the tilt it gets of 23.4 degrees, then if the earth is around here, these countries, the United States, Canada, Finland, Sweden, etc., they face away from the sun. They get cooler. We are feeling some cool environment now because the place is cloudy. And because it has gotten cloudy, it will be cool. And when it gets cool, it means that if you didn't have any sun at all, because this part has tilted away, then it becomes winter. On this other side, you have these parts also still far away. In June, these parts of the United States face now the sun, becomes summer. In September, you transit into, this should be autumn, what we call fall. Autumn, fall, winter, spring, summer, like that. So you have that sequence of autumn, winter, summer, spring. No, you have autumn, winter, then things spring up in the plants, then you go to summer. Autumn, winter, spring, summer, like that. I think we are as fake as we are because everything is okay. Everything is available. Like we are trying to say in the morning. That for us, 6 a.m. in the morning is wake up. 6 p.m. is go to the house. So it's the same day and day in, day out. But if you were in these countries, it is not business as usual. In the winter, at around 2 or 3 p.m., the deep winter, the December, it becomes dark at 2 p.m. In the morning, it is dark until 10 to 11. So things have to change. You have now to start carrying a watch to know the time. Otherwise, you cannot say, by the look of the sun, it's about to set, so that is 6 p.m. No. So then, but in the summer, when it comes to June, countries like Norway, Finland, Sweden, or what we call the Scandinavia, it can reach up to midnight when the sun is just setting. And it sets for a couple of minutes, around 2 it is up again, 3 it is shining. So again, you can't say, that's why I think one professor from the United States couldn't teach in Tromsø, in Norway, because it was day, all night, all day. They gave him a blinder, nothing. They got him hardcover curtains to bring darkness in his apartment. He refused. Things couldn't work for him, he went away. So in winter, you are always sleeping. It is dark, you want to sleep, even it is so cold. In summer is the reverse. They think you don't even feel any sleep up to midnight. So that's how things happen because of these seasons. Now, but all that comes about because of evidence. So someone will say that, okay, who said the earth is round? It should be a square. After all, Galileo was killed because of he was killed. Galileo was killed because he said the earth is round. They say no, it's a square. So he was. So in that perspective, the International Space Station is one of the available avenues now that someone who is so adrenaline can be taken there if it wasn't about the cost, so that he or she can be able to see how the world looks, how the earth looks. And the International Space Station, as I said, is a bunch of modules. This is its robotic arm. But my interest is to show you that this horizon here shows you that the earth is round. Similarly, you also see it is round, the clouds are there, they do not escape. Anything that evaporates from the water surface here, either in the lake or sea, still comes back. Because in order to escape our atmosphere, you must have about 11 kilometers per second. What you will be taught as escape velocity. So in order for a rocket to be launched and escapes our atmosphere, maybe goes to heaven, if it is there, is that you have to use 11 kilometers per second. You can convert that how many per hour would be. And so this is still modules, this is the sun. So this International Space Station was built by a bunch of, a fleet of space shuttles. There was Discovery, there was Columbia, which got an accident and everybody died. There was Endeavour, there was, this is Discovery, Columbia, Endeavour. I don't remember the other ones, but I think there were a set of 5, and they did this for over 30 years. They got retired in 2011 or 2012. 2011 or 2012. I have to get those dates, those years clear. So this also has 2 rockets and also has a fuel. This is a fuel tank. So these ones propel it into space. When it is about to reach the end edge of the space to escape, then this one is detached and it comes back and lands in the Pacific Ocean, and they get it and repair it and use it. So are these ones. So we don't lose anything. The launching is near the water, and it is calculated that by the time they are, detached off, they'll be able to come back and land in the sea. When it lands back to the airport, it cannot now fly here on Earth and starts flying around, moving from place to place. So what they do, they put it on this giant plane to be transported to other places. Most especially when they were transporting some of them to, I think, Kennedy Center, Kennedy Space Center, for either keeps or for repair or for research. They use this kind of plane transport. That's so we are able to use the International Space Station to believe that the Earth is round, is a round object. And the Earth, geographers talk of the iron core, then I don't know what this one how they call it, and then underneath us we have this magma here, this molten magma, whereby whenever it gets a chance, it just spits out and causes volcanic mountain. So it comes out as a volcanic action. And then you get the Ngaingas, you get Kivu, you get all those mountains that produce magma. But it's a fact that the Earth is round by all measures, and astronauts who have been on the International Space Station, most times, not most times, but at times they fly above the Earth, other times they fly below the Earth, and it is not a small thing. The International Space Station is not a small thing. As you can see, these panels here are adjustable depending on where the sun is. So they track the sun's direction to be able to provide efficient amount of. So it's the National Space Station is a bit larger than a precise soccer field. Soccer field is where the Americans play their football, what they call football, much as they play it using their hands. I don't know why they call it a football, but fortunately enough they call it soccer. Just see them running around with this ball which they throw and it spins, and then another one grabs it and flat like rugby. That's their football. So it's a size. This is another graphic shows how it looks like from the other angle, and if you put it on that soccer pitch, this is how it looks. And the soccer pitch is about 100 by 50 meters, which is huge, something like that. Now, astronauts are trained using the water, big swimming pools. If you watched the movie called Armageddon, you'll be able to see how those astronauts were, those guys who were drilling, who were working at an oil company, how they were integrated and trained on how to be astronauts. So you go in your space suit. Space suit should be sealed everywhere, so it means you wouldn't care about the water. But this is how, if you wanted to experience the concept of weightlessness, then you go in a swimming pool. If you go in a swimming pool and you are there, you cannot walk like this in a swimming pool and you go comfortable, or in the lake. The moment you start doing that, they see you now floating on the water. So that's why when you are on the frame in the swimming pool or in water, you try to make sure that your feet, if you are at the shallow side, you make sure that your feet are on the floor. That's where you can easily go. That's how also astronauts move. So in 2015, Kelly, when he was, I think he was launched late 2014. Nah, either in 2015 and came back. I think he was launched in 2015 and then he came back in 2016, I think in March. He's called Scott Kelly. He has a twin brother called Mark Kelly, and he had to spend a year in space so that they can investigate how does space affect people's bones, or flesh, or blood, or whatever. And it is believed that he grew a bit taller by a couple of inches, I think 125. And he spent there 1 year, and 1 year would be able to, he would have moved around the earth close to the distance that he would take to go to Mars. So he flew with these two Russians, and before you fly to space, you have to sign some agreements. So here they are on that mission of signing a couple of agreements. Probably they will tell you if you die there, we shall take all your property. I don't know. Whatever they were saying. But Scott Kelly was able to see 10,944 sunrises and sunsets, and this would be during his year in space. If you went to Twitter and you look for, or even Facebook and you look for this hashtag year in space, you'll be able to get a recap of all the information that was shared about his mission, year in space. For us, we only see about 684 sunsets, but for him, you will see 10,944 in 1 year. And the International Space Station travels about 7,500 miles per hour, and that means that it orbits the Earth every 90 minutes. So every 90 minutes, the International Space Station has already gone around the Earth. 90 minutes. And this will give about 16 sunrises and sunsets each day. Then you do the math of a year, which is about 365. So if you go to NASA.gov /1 year, you'll be also able to get some information about the year in space mission. So he's with Scott Kelly, is with his Russian friend, colleague. And Kelly was able to look to travel, being that he was orbiting the Earth, going around the Earth every other 9 minutes. He was able to move about 143,640,000 miles during his year in space. He was conducting research to prepare us for our journey to Mars. And which is about, the journey to Mars is about 3,640,000 miles less, which is then 140 million miles from Earth. So in the National Space Station, this is again another small information to give you a perspective of what his travel means. And water is a precious and limited resource in space. So in the National Space Station, crew members recycle whenever it is possible. And this includes even recycling their urine. So they urinate in a very nice place to make sure that they can recycle their pee for this part. So because Kelly would have to use 730 liters of recycled sweat and urine during his year in space. And this is when they were now heading for launch, for the launch mission. And this is where the rocket is launched. And they were launched in this rocket. Here is Scott in space, trying to take a couple of shots. And he was pondering that he had been in space for 3 days, and if he was to be on a mission to lunar orbit, that is to the moon's orbit, he would be already arriving. And if he was to be on a Mars mission, he would have a couple of 267 days to go. That was then. The time when this photo was taken. And you could follow him on Twitter, _CDKRK, or you just follow the hashtag. This is his Instagram, but this is for hashtag AI in space. You get more information about what it is. Or you can use the hashtag Journey to Mars. So this is Kerry in space. He was giving himself a shot. This is the inside of the space station. They were able to grow some plants there and monitor how they behave. Do they also have leaves which are going upwards? Do the leaves go downwards? Do the plants become short because there is no gravity? Do they become taller because there is no gravity? So they were trying to look at all those, because if you are going to go to Mars and try to grow food there and other activities, you need to know how those different things work in space. And you can only do that at the International Space Station. So this is a nice flower which was grown in space, and he came with, I think, some. And the other one should have been, I don't know exactly what the other photo was about, the video was about. But this is the moon. This is how the moon will look like. Tonight, the moon will be a little bit larger, maybe up to here. But these are the craters which are created after space junk or space rocks hammer it. But this photo here is basically to show the transition of the International Space Station across the moon. And this is a photo taken by a satellite of the moon up there in space. Another photo. This is a photo showing the sunset and the new moon still when the photo is taken from space. I should have a 2016 calendar, but this is a calendar to show you different days of different months, for different months, for a given year, like now 2015, and showing you exactly when is the moon new, this part here, and when is the moon full, this part here, and this part here. Okay, so what's up January? This was supposed to be January, and in January I gave this presentation. But this is to show you can go on the internet and find out when the moon is setting, when it is rising, and the exact time, and the distance from Indian person, and what percentage of the moon is illuminated. Now, what the hell, or why the hell should we care about the moon? The moon is the influencer of a couple of things. First of all, it protects us from the space rocks, space junk. What should have come and just come to us and hit us, it just goes for the moon and boxes it. Because when they come, they are at large. When they go near the moon, they get attracted to the moon before they actually get attracted to the earth. Because the moon, when you have two bodies, gravitation dictates that, or the law of gravitation states that any two bodies attract each other, and the force of attraction is proportional to their mass, and inversely proportional to the product of their mass, and inversely proportional to the distance between them. So when these rocks are far away, no problem, but when they come nearer, the force increases, and then they start hitting the moon. That's why we got those craters. So it protects us in one way. The other way is that when the moon is either full moon means that the earth is here in the middle, the sun is this side, and then the moon is this side. Remember, the moon does not produce its own light. It only reflects the light from the sun to the earth. So if we are the earth, it is in the night here, day for these people, so the sun has disappeared this way. We see, because the moon is somewhere that far, we see all the sunlight reflected back to Earth, and you get a full moon. But that means that you have the sun this side, you have the moon this side, and then they shake the earth. When the earth is shaken, then we get what we call the tides. When the tides, if you were on a Navy beach, you will see water coming on the shore. This water here, when it comes on the shore, it doesn't all go back. If it is sunny and it is hot, some parts of this water evaporates. And that's why either in full moon, like now, full moon will be on the 20th. But as you can see, we already have some clouds. But on the new moon, apart from this new moon really of this ED, I didn't see any rain. But mostly on the new moons, you'll get a drizzle late in the night, 3 a.m. there. Because what would have evaporated from here will condense. After condensing, it drops back. Then we got the, it's all about the...
So, if the moon was taken out of space, would the rivers on Earth flow?
We may even fly away. They will flow, but you see these tides, if I didn't say the word tides, these tides which you hear is not, the river doesn't flow because of that. But they only, the tides only make the water ping pong on the shore back, and whenever it is going back to the lake, you don't get all of it going back. That what is left evaporates, and every time it evaporates in the night, then it collects. That's why lake regions around Lake Victoria, when they are announcing the weather forecast, they say it will be some rains around the Lake Victoria basin. It's because of this effect here. I've never been to Mombasa. Maybe in future I'll get there, but they say in Mombasa, at one point in the year, you find that the shore is like here. At another point in the year, the shore is 5 kilometers deep into the water because of this effect of the moon. So it's all about the sun, the moon, and the earth. These are the three bodies that help us. So comparatively, if you look at the moon and compare with the numbers of the numbers, this is the diameter of the moon, and then this is the diameter of the earth. But graphically, on scale or to scale, this is actually how the moon compares with the earth. On scale, this is in reality. This is a photo which was taken by a satellite as the moon was going around or going past the earth. So comparatively, this is, so you will probably stick in about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, maybe 13, maybe 15 moons in one Earth. And this is what happens. What happens is that you have the Earth which is spinning about its axis, tilting 23 degrees at least at one point, and then you have the moon going around it. So what happens is that you have also the sun spinning about its own axis for 11 years, something we call the solar cycle. So for example, between 2008 up to probably 2013, 14, 15 there, we were subsiding into the minimum, whereby the maximum should have been around the maximum should have been around 2011, and that's why we had a lot of lightning. But people haven't agreed that, or people haven't been, they haven't accepted that actually when you look at the causes of lightning, space charges, which we call space weather, is also an effect. And they are always produced from the sun due to the due to when you have sunspots and then they spew out particles, which we call, always the sun produces solar wind. If you are on a campfire, you see plants' leaves shaking because of the plasma. Fire is plasma. So, and that fire produces a solar wind. It produces a wind. So the sun produces that wind always. And that wind always blows towards us. But anyway, the moon will go around the earth for about 30 days. And the two of them should be able to go around the earth The moon goes around the earth for 30 days. The earth goes about itself for a day, 24 hours. The period or the time for one revolution around itself, that should be 24 hours. Then the moon goes around. So the reason behind is that as we move around ourselves for one day, the moon is going slowly to cover a whole month. So we sometimes leave it there, it sets, we go continue, find it somewhere and see it. So around 7 in the evening or 5 in the evening. Then we see it until probably 3 a.m. we leave it again. So we keep doing that in the year. But every time in a month. But every time we find it, we tend to look at a given point of it, whereby at one point we see a crescent. At another point we see it when it is a new moon, how should I call it? It's a crescent, then you have quarter moon, then you have waxing gibbous, you have waning gibbous, then you get to the second quarter. We shall see those different descriptions. Okay? So if I was to time when the moon touches this side, I will start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Approximately. So you have 12 months in a year. It's not so accurate. But as you can see, if I time on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13, 12, so close, okay? Actually, it should be 13, but we know that we have 12 months, isn't it? Okay, so basically I have already talked about this, isn't it? The different seasons, we have the sun there. And then the earth it does not spin in the vertical direction, in the vertical position all time through. It tilts at one point, and after tilting, then we get, that's why the seasons come up. And this is another part showing the solstice, the solar solstice, autumn. So I remember we said this will be autumn, the winter, then this will be spring, summer. These are dates to show you. 21st December, you have this in one line. The sun, the sun and earth in a straight line along this point will give you the winter. Then here you have the autumn, the spring and autumn, and here you got the summer. Oh, now you click it. Yes. Then we got another one with the winter solstice, vernal equinox, then autumn equinox, and summer solstice. size. These ones are called Mars. Now, the rationale is that the moment that the Earth spins, tilts, and comparatively look at the line, then these countries here will be away from the sun, and these countries will experience the winter. The ones down will experience the summer. 6 months later, when you are on the other side, then you get these countries facing the sun, becoming winter, and then you have the other ones becoming summer. And it doesn't only occur for the Earth alone, it also occurs for these other objects, the asteroids and the other space objects. So we have this part being in the winter, 6 months later the reverse happens, these other parts here face the sun, become summer, winter. Comets also experience the winter and the summer. This is an actual Google Earth map. Google Earth is able to give you cellular images up to the level of resolution of about 10 meters to a given about 1 kilometer. It's up to you you can zoom up to a given number of, up to I think 100 meters if you have a good picture that was taken for a given location by the satellite. So if you look at the Earth using Google Earth, this is an including the Earth in the first quarter. But this is not artistic impression. This is real. This was live on CCTV, Chinese cable TV news, and it was live. So they were showing the robot going around and the surface of the moon. And this is just to show you the orbit of the moon around the Earth is not a perfect orbit. Sometimes you find it goes there, until when it is in a straight line with the sun, and then you get an eclipse. This was I think Jupiter. This was I don't remember which. And so this was a photo shared by some people to show the conjunction of these three objects. Maybe this was Mars. I don't remember very well. This is called the Hubble telescope. It's a telescope which was launched into space to take photographs of deep space and search out for more planets. They also launched the Kepler mission, which uses the Kepler laws. Kepler laws are that planets move around the Earth and the Sun and describe the path called an orbit. The squares of time is proportional to the tubes of the square, I think, to the tubes of the radius, not radius, but the distance swept by the distance between the planet and the Sun. And the third one, there are three. The third one, I don't remember what it says. When you grew up in S5, S6, you were able to learn it. But the Kepler mission has done a tremendous job. This is the eyepiece and the objective of the Kepler mission, and these are panels to provide electricity for the electronics we do. And a couple of planets have been found out. We got Kepler 62e, which is 0.82 of the Earth at 1, Mars at 0.64, Neptune at, and Jupiter is this whole Jupiter. So this is a comparison of the new discovered habitable or potential habitable exoplanets. Exo means that they are beyond our solar system. And this is probably tonight we will be able to see this Jupiter and its moons. And we always look at Jupiter in the skies and think maybe it is a star. So is Mars. Mars also these days is up there in the sky, so we think that those are stars. The yellowish, orangish, or reddish star you see, that's Mars. On this other side, far away a bit, is what we call Jupiter. So you have the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then we should be adding Pluto around there. And these are the moons associated with the different planets, and this becomes our solar system. Planets look different. If you look at the way they look, this one looks bluish, this looks sky bluish, then you've got combination of these desert fire. The ice is blue waters, and then you got taken out of as you cut it away. The reason behind is because of the composition of the gases found on these planets. Okay? And these the gases which are found on these planets, they constitute the way the planet looks like. And that's why in this graphic you have Venus looking this hot, you have the moon this white, Earth looking this way, Mars looking that way, and then you have Jupiter, Saturn, Mercury, Pluto looking like that. Pluto is a dwarf star, a dwarf planet, it's very tiny. But the wooden dwarf planet is also far away. That's another problem. So far away, it is at the edge of our solar system. Now, the rains on different worlds. If you are on Earth, where we live, the rain is water. If you were on Venus, too bad for you. The rain there will be sulfuric acid, so I don't know what kind of umbrella you will use. If you were on HD 189-733b, which is one of the exoplanets which have been done, you have glass as the glass is your rain. If you are on Neptune, you will be able to have a diamond. So I think every rich man should live on this planet. You would have that TR56b, you would have iron, and the Titan will be having it. The solar system is complex. It's a complex phenomenon. You got all this stuff being there in space, and you have Saturn here, you have Jupiter, you have Earth here. And as you can see, this is the complexity of the solar system. This one is spinning here, spinning there, another object slowing down. So the complexity of the solar system is what is enabling scientists spend sleepless nights studying A, B, C, D, up to C. And of recent, a new phenomenon has been added into the issues to do with space exploration and space understanding, and these are called gravitational waves. They were able to detect them now, I think, for the third or second time. It may bring a new way of looking at stuff. And I talked about the perigee moon when it is near to the earth, and this is the kind of, if it is at the horizon, like when it is rising on the horizon, you get an illusion of being a super full moon. So you get this bunch of cactus trees, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all filling in. You can imagine the cactus trees shouldn't be all these many in one moon. If you compare the road, I mean a bunch of trees, you have about 4 trees all fitting in one moon. Or a road, if you compare the size of the road here and compare with this kind of relative to this distance, how the road is becoming thinner, but you still got the moon being that huge. Or if you were to be on a beach and you look at the other side of the waters, you can see how huge it is. It's called a super full moon. It happens once in a while in a given year. In a year you can have a bunch of them. And it is a good sight to look at, finding that it can house a whole building, and you see a building fitting within the moon. And scientifically, you got, this is the Earth here, and if you, in magnetism, in your O level, in your physics, you were taught, or you have been taught that the Earth has a magnetic field, so it is as though it's a giant magnet. So if this is our Earth, and you have your Africa here, with other countries the other side, with our tilt in consideration, you have this being the north, and you have this being the south. So it is as though you have a huge magnet inside there. So you have a bunch of, a ring of the magnetic field lines moving, of course, from the north to the south. Okay? If we talk of the configuration. And then you have this is the same thing here. This is what we are having here. We are having these magnetic field lines forming up our what we call eventually this region. This region here is what we eventually call the magnetosphere. It comes from 2 words, a magnet from magneto, and then a sphere. It's a sphere because it is going around the earth, okay? You have all that region. The magnetic fields are coming from the north, they go here, they go there, they go here, they go here, they go here. Meaning that they create a sphere around the earth. That's why we say magneto. So we say magnetosphere. Magneto is, you have a magnetic field, but those magnetic fields are creating a sphere. So we call them magnetosphere. So it means that if you had the sun here, okay? If you had the sun here, and it produces its wind, and this wind is a stream of charged particles. In physics still, you find that we tell you that when you have a current moving in a conductor, which is being transported by positive charges, when these charges are moving, you get, if this is a current direction, you get a magnetic field around that place. So it means that if you have streaming charged particles, then a magnetic field is created around them. When that magnetic field is created around them, that field, this field here, interacts with this field. That's why on the comparison here, you have this being our sun, and you have these being parts of the particles which are produced. Sometimes we call them CMEs, coronal mass ejections. Then they compress this other side of the magnetosphere, whereas this part here, because of the streaming charged particles, gets elongated. So assume a girl is riding a bicycle and and she has a lot of hair. Or assume somebody is putting on a scarf. The scarf will be forced to fly behind. So comparatively, you will be able to get, as this person goes around on the bike, the hair or the scarf will be going backwards because we have the wind streaming from this side. Okay? So when that happens, then we get this kind of condition. That's so why we have SDO, Solar Dynamic Observatory, we have ICON, IMI, the expander, Van Allen probes, TENS, Wing, AMES, JOTEL, JAXA, this is Japanese. Then ID, Cell 1, Solar Orbiter, ESA is European Space Agency, Solar Probe, Voyager, SOHO, Solar Heliospheric Observatory, for this is also for European Space Studio, RES, to mention a few. All these are satellites sent to space, and these all create jobs. There's somebody who has to analyze the photographs, somebody who has to analyze the data, somebody who has to keep monitoring it, hence the jobs. So if we don't create those different revenues, like I was telling you, if you have a fence and somebody has to manure it, or is put fertilizers and manure, that's a job. But someone has to manufacture it, someone has to transport it, then someone has to trim it, has to buy a trimmer, then someone has to manufacture trimmers. Then you create jobs. But you don't just say there are jobs to do what? If you can't mop the place, you can't color the place, so where are you going to get a job? Then finally you have these rockets also, these different satellites or space called them spaceships were launched, just like we launched the rover on the moon, or the cages to the space station. And this is an example of the magnetic probes which are studying the magnetosphere. This is the Earth. Yes, this is graphic. This is the sun here. And they are trying to study the different properties of the magnetosphere. And this is a typical satellite, which can be, you can use the fuel to readjust it into the orbit, but most of the time it uses the solar panel. This inside here we have a transponder and electronics, and this is the satellite dish for the. So we call it a satellite dish, the one on our houses and on our banda and hotels and bars. They are satellite dishes because they get information from the satellite. So what happens is that this is the moon, this is the Earth. So a station, a TV station, probably MTV, will send its signals to the transponder of the satellite. So on the satellite it has both capacity of receiving and transmitting. So it receives, then after receiving, then takes the people who need it. Because the satellite is so far above in space, it is able to send it to a given particular area. Previously, what would happen in communication, especially the analog communication, is that a station like MTV, but let's use like UBC, which was the owner of the Kororo mast. This would be, if we say this is Kororo, okay? If this is Kororo, and then we have the mast there at Kororo, then we would have a transmitter on the mast of Kororo, and our Earth has an atmosphere, and this atmosphere has layers, but the important layer is the ionosphere. Also coming from the word ions, ion for ions, and then a sphere of ions around the Earth. So the station UBC, or it used to be UTV, but UBC would send these signals into the ionosphere. But because these are ions, okay, so it means they are denser compared to this one, which is less dense. Which one is denser? So have you studied the total internal reflection?
Yes.
When does it happen?
It occurs when the angle of incidence is greater than the critical angle.
Yes, so but in which medium is the critical angle? Is the wave moving from dense to less dense, or denser to less dense?
It is moving from...
Anyway, did I ever ask you the question of why do we get louder in the night compared during the day? So in the night we have the air near the Earth's surface having cooled down. And when it has cooled down, it has gone down, meaning that now the warm air is a bit up. So you have to be moving from, like a mirage. The mirage happens because the air near the surface is heated up. Immediately when it is heated up, it flies above and the cold air comes down. And it means that total internal reflection happens from which medium to which medium?
From denser
To less dense. That's what you think.
because the light ray is moving from the sun, which is up.
But even if you don't go far, let's look at this scenario. This is the normal. And we are having, first of all, if you are moving from denser to less dense, okay? If you are within less dense, if you go crossing, where does the emerging ray go? Towards the normal or away from the normal? Away from the normal. So if you were here, it will go straight. If you were here, it will go straight without. If you turn here, a little bit here, it goes, so it means it keeps going this way until when you have gone past at the critical angle, when you are at C here, then it goes along the inner face. If you go past, if your eye becomes greater than C, then it means that you are now going to get total internal reflection. So yes, when it is moving from denser to less dense. So as you get these waves going through the ionosphere, as the waves are about, of course, to cross I told you this one is more denser. These ions are more denser. So as it is about to cross to go above into the skies, if we drew a tangent here, then if this one is above the critical angle, it comes back to the earth. And then if it is a radio or if it is a TV, so it doesn't matter, whichever it is. It could be a radio, okay, or it could be a TV. So that's how waves come back. That's how waves used to be transmitted in analog, using the ionosphere. And that's why when you will be listening to a shortwave radio or medium wave, when it is raining, I don't know whether you have ever listened to a shortwave radio, and soon people will not even know that there was analog TV, where a picture will be having shade everywhere. So, but when the lightning would flash, you will hear because you've tried now to interfere with the amount of ions there. Because lightning is an electricity. So when it affects this, that's when you hear But when you use FM, frequency modulation, the thing comes from the station straight to the radio. Straight. That's why if you have a hilly place, and if it is far away it won't reach, so you have to reboost. If you have Capital FM, you go to Mbarara, they have to reboost it. Get a signal from here up to Mbarara, maybe transport it with the internet, and then you broadcast it to the public. But then, with the evolution of the satellite sends a signal. So in transmission of satellite signals are given a critical, I think above 3 gigahertz, and it is able to cross through the atmosphere with no problem, and goes to the satellite, and then the satellite is able to also send it to the TVs. There are consequences at one point. There are consequences that as the sending it back, if the ionosphere here is enhanced, it will affect it. If you have a cloudy condition, you've seen when it is cloudy, scatter, you see images freezing somehow if it is raining. It's because of the satellite signal failing to penetrate through the clouds comfortably. Yes. This is the bottom line space weather. What I've been talking about here, the ionosphere. This is our ionosphere here. So if we have an event of space weather, that is when you have a big chunk of charges coming from the sun. Then this chunk of just a moment. This chunk of ions can affect the radio wave disturbance. They can cause disturbance. The earth currents can cause the pipeline to get a problem. The GPS stations can be affected, from GPS to our GPS handheld receivers or in the car. The grid, our electricity grid can be affected and disrupted. Our optic fiber cables can get affected. Our pipeline, the pipeline of, you've heard about the Millikan oil experiment, that an oil drop can be charged, can acquire charge. So if you have a pipeline with oil and you have charged particles moving around it, the oils can get charged and get stuck to the walls, eventually stick there and it becomes constrained, bursts. The grid, it can overload the space weather, can lead to overload of the grid, and then you cause accidents. Then you have rainfall, water vapor, causing delay of the satellite imagery. Astronauts can be in problems. Then these all can affect our technologies due to what we call space weather. Conditions around the sun that affect the technologies in space and on Earth, and can even cause death. This is another way of doing photography with the moon, with the plant. And I told you on one of the occasions, Earth is between the sun and the moon, the shadow cast by the Earth can land on the moon and cause a land on the moon. What I normally show people before I take them out on a telescope, and then when we go to the telescope, they know what they are looking up to. Have you learned anything?